It's 14.18.
All right, it's 5:30. Let's go get started. All right, good afternoon, everyone. How's everyone doing today? Doing good, hanging in there. Okay. End of week 8, so we're I guess we're more than halfway now, so we're definitely chugging along. Okay, so today I think it's gonna be very short, and so the only thing I want to cover today is just an example. And so last time on Tuesday we kind of went through the entire process of the direct stiffness method, and so today you're going to see it in action in an example. Okay. And so that's all I have planned, and so I think that should only take maybe about maybe like 20-25 minutes. And then just like I said on Tuesday, we're going to spend the rest of the time today just helping you guys out with activity 4, because I know quite a lot of you had some questions, and so I know there's some people in here. So my plan is to leave that time to go help people with activity 4. And if you're on Zoom too, we can do a screen share, and so I can help you out on that way too. But I wanted to make sure I give you guys enough support with that so that you can finish that activity and then focus on the project after that. Okay. Okay, and so that's all my announcements. And so are there any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off on Tuesday with the direct stiffness method. Right. And so on Tuesday, we introduced this idea of the direct stiffness method as a way to implement finite elements. Okay, and so we've already talked about that. Finite elements is basically just a way for you to take a differential equation and turn it into an algebra problem. Okay, so there's lots of different ways you can do that, and the way that we are learning first here is the direct stiffness. Okay, and so before we do the example, I want to summarize all the steps that are involved to not only solving an FEA using direct stiffness, but just solving any kind of FEA, in general. And so of course, ANSYS makes this a lot simpler. And so ANSYS makes it so that you don't have to do a lot of these things. But underneath the hood, ANSYS is doing these things. And if you're going to solve an FEA problem by hand, these are the steps that you would have to follow. Okay. Okay. And so the first step you're going to have to do, and most of the time, for this class, this step is going to be done for you, is to discretize the geometry. Or discretize the problem. Okay. And so all I mean by that is to take your geometry there and then just break it up into elements. And the next important thing is to label all the elements and nodes. Okay. And so anytime you do a finite element problem, there has to be elements. And so step 1 is to get you those elements. Okay. So step 1, it's when you're using ANSYS, this is basically what's happening when you're meshing. Okay. And so when you're meshing, we know that you take your geometry and you break it up into all of these little finite elements. But what you don't see, underneath the hood is that ANSYS is actually labeling all these elements. They all have their own specific ID number or ID letter or some kind of identifier for them. Okay. Okay, and so once you have your geometry all discretized and everything is labeled, the next step is to form the element stiffness matrices for each element. Okay. And so every element in the in your geometry, depending on the type of element that it is, is going to have its own element stiffness matrix. Okay? We've only gone over one element so far, which is just a spring. But over the next few weeks, we're going to introduce different types of elements, and we're going to see what those element stiffness matrices look like. Okay? Okay. The next step is that after you get all the element stiffness matrices is to assemble all of them into one global linear system. Okay, because remember the point of FEA is to get an algebra problem out of this, and so that global linear system is our algebraic system of equations. Okay. Okay. The next step is to apply boundary conditions to the global linear system. Okay. And so even though at the end of step 3, we end up with a system of equations, that system of equations actually can't be solved until we apply boundary conditions. Okay. We're going to apply our constraints, we're going to apply our loads, okay, and that's going to modify our linear system. But then it's going to give it, and so as long as we do that correctly, we're going to end up with a system that we can solve. And then once we have that system primed with the boundary conditions, we're now ready to solve it. Okay. And don't worry, I'm not going to make you solve these big linear systems by yourself. I'm going to show you kind of a quick and easy way to solve this in MATLAB, so that you don't have to do 10 equations in 10 unknowns. Okay. Okay. And I know the aspect of MATLAB kind of is a little bit intimidating, but don't worry. It's literally just like 3 lines of code. Okay, and I'll show you exactly how to do it. And it's basically exactly the same for every single problem. Okay, we're only going to use MATLAB just to solve the linear system, and there's kind of a simple way to do that. Okay. Okay. And so what I'm going to do, and so for each of these steps here, I kind of wrote a long description so that you'll know what they mean. But I think it's a lot easier to kind of remember them in terms of their keywords. So I've went ahead and I've underlined kind of what I think is the most key word in each of those steps. Okay. And so step 1 is to label. And so you're going to get all the elements and nodes, make sure they're all appropriately labeled. Step 2 is element stiffness matrices for all the elements. Step 3 is assemble. And so you're going to assemble all the element stiffness matrices into one. Step 4 is boundary conditions. And that's going to modify the linear system. And step 5 is to solve. Okay. All right, and so this is basically the method that we're going to follow, over the next few weeks. And this is kind of a good general purpose, algorithm to solve any FEA problem. Okay. And like I mentioned before, there's lots of different ways to apply FEA, and lots of different ways to to do it. ANSYS does not use the direct stiffness method. I will tell you right now that. And I've looked at a lot of FEA codes, and so I've looked in the guts of, a bunch of research codes, and I'll tell you that the only thing that's different about FEA codes is step 2. And so step 2, which is how we form the element stiffness matrix, that's going to be the primary difference, but everything else is going to be more or less the same. Step 4 is, different people have different ways to do it, but they all kind of do the same thing. But the main difference is in step 2. Okay. And so even though a lot of people look at the direct stiffness method as something that's really simple and not really practical, you're really getting I'd say 80% of the whole process. The only thing you're missing is just step 2, and that's where kind of a lot of the intense math is. Okay. Okay, and so in the example that we're going to do next, you're going to see that we're going to follow all of these processes exactly as they are. Okay. Any questions on this before we jump into example? All right, so let's do an example here where we can see this in action. Okay, and so let's consider the following system of springs. All right, so we're gonna have a fixed wall here on the left. We're gonna have one spring that comes off just like that. And we'll say the spring has a spring constant Ka. This spring here is going to be attached to a block. And this block here is going to be attached to two springs. So the top spring, we'll call it KB. One string we'll call KC. Okay. And then on these springs here, we're going to apply forces. So we'll say we'll apply a force in this direction. We'll call that F3. And then we'll apply force in the other direction on the other node, which we'll call F4. Okay. Okay. And so let me go ahead and define all the parameter values here. So let's say Ka here has a spring constant of 500 newtons per meter. Kb has a spring constant of 100 newtons per meter. And Kc has a spring constant of 250 newtons per meter. And F3, F4, we'll say F3 has a magnitude of 100 newtons, and F4 has a magnitude of 50 newtons. Okay. Okay, so there's our situation. And so what we want to solve for is we want to solve for the displacements of all of the nodes in this in the system. Okay. All right, so there's a setup for our problem. So we have three springs, and of course, those three springs are going to be our elements. And then we need to solve for all of the nodes, the displacement of all the nodes in the system. Okay. All right, so let's go ahead and follow the recipe that I laid out before. So first thing we're going to do is we're going to label everything. Okay, so the system is already discretized. You can tell that three elements here are going to be three springs. The only thing that we have to do now is label all the nodes. Okay. So the node that's attached to the wall, we'll call that node 1. This part's actually a little bit confusing to people. So, I put that wooden block there to tell you that all the springs are going to be attached at that point. And so that entire wooden block there is going to be node 2. Okay. Okay. And the reason we can group those all those nodes together in 2 is because they're all going to move together. Okay. And so the wooden block kind of makes it so that they're all kind of rigidly attached to each other. Okay. The top free node, and so the one that's on the right, that's being acted on by F3, that's node 3. And then the bottom free node, the one that's being acted on by F4, we'll call that node 4. Okay. Okay, and so everything's labeled. And so we have our three elements. And so our three elements are going to be our three springs, Ka, Kb, Kc. And then we have the four nodes in our system, node 1, node 2, node 3, and node 4. Okay. All right, so we're done with step 1. And so we've gone ahead and we've labeled everything. And in fact, in this problem, we have all the parameter values as well. So are there any questions on just the setup for the problem so far? Okay. All right, so let's go ahead and keep going then. And so the next step is we're going to write out the element stiffness matrices for all the elements. Okay. And so we have three elements here. And so we have three, because we have three, three springs. Okay? And so we're going to start with element A. And so remember, the element stiffness matrix for a spring is that we simply just take its spring constant, Ka, and we arrange it like the following. So we have Ka minus Ka, Ka, and Ka. Okay. We're going to go ahead and fill in the values for that in a second. But remember, the other thing that you have to do when you form the element stiffness matrices is you have to indicate which nodes the element is acting on. Okay. And so I'm going to call this D1 and D2 because they're acting on nodes 1 and 2. And this is, of course, going to equal to F1, F2. All right, so let's go ahead and fill in the values for Ka. So we have F1, F2 is equal to 500 minus 500 minus 500 times D1, D2. Okay. So that's the element stiffness matrix for element A. Okay. Let's go ahead and do the same for element B. And so element B up here, you can see is attached to nodes 2 and 3. And so we're going to have F2, F3 is equal to KB here is 100. So we have 100 minus 100 minus 100 and 100. Okay. And then this is going to be attached to nodes 2 and 3. Okay. Right, and then finally, we can make the element stiffness matrix for element C. Okay. So element C is a little bit unique. And so, if we look at element C right here, okay, you can see on the right-hand side of element C is attached to node 4, but on the left-hand side, we're actually attached to node 2. Okay. And so, I think when you're doing these kinds of problems, it's kind of tempting to get into a rhythm. And so element A is attached to 1 and 2, element B is 2 and 3, and then you would say that C is attached to 3 and 4, but you have to look back at the figure and see that element C here is actually attached to nodes 2 and 3. Okay, so this would be F2, or excuse me, 2 and 4. So F2, F4, okay, and this is equal to 250 minus 250 minus 250. And 250. Okay. And then that's going to be acting on displacements D2 and D4. Okay. Okay. All right, so those are all the element stiffness matrices. And so the next step is going to be assembly. Okay. So any questions on these so far? All right, so let's do assembly now. So remember, for assembly, we want to put all of these into a single big linear system. Okay, so we have four nodes overall, and so our global linear system here is going to have 4 rows and 4 columns. Okay. So on the left here, we're going to have F1, F2, F3, F4 is equal to, I have a big matrix here, D1, D2, D3, D4. Okay. And just to help us out, with the assembly, I'm going to go ahead and label the columns. And so from left to right, we have D1, D2, D3, D4. Okay. And so the task of assembly, remember, is to take all the element stiffness matrices and insert them in the right locations into the global stiffness system. Okay. Okay. And so the nice thing is that, I'm working on an iPad here, so I can use different colors. And so I'm going to use the colors to highlight the different regions. But just know that, in your notes, maybe have some way, maybe use different line markings to show you, which elements go where. Okay. Okay, so let's start with element A. So with element A, we know that acts on nodes 1 and 2. And so that's going to be the first and second rows and the first and second columns. Okay, so I'm going to go ahead and box that off. Okay. So inside that box, you'll notice it's a 2x2 box. We're going to insert the entries of KA or element A. Okay. So we're going to put 500. Minus 500, minus 500, and 500. I'm going to leave some space there because I know we're going to have a lot of overlap on that spot. Okay. Okay. Next we have element B. And so element B, from its element stiffness matrix, we know that's going to be nodes 2 and 3. Okay. And so nodes 2 and 3, that's going to be columns 2 and 3 and rows 2 and 3. Okay. Okay. And so the area of the global stiffness system is going to be exactly that. Okay. And so we're going to add in all the entries. And so for element B here, we have 100. So it's going to be minus 100, minus 100, 100. Okay. And then remember, whenever we overlap, we're going to add the entries together. Okay. So we have 500 plus 100 on that overlap. Okay. And then we come to element C. And so this one's a little bit more complicated because we don't have nodes that are right next to each other in the system. Okay. So for everything else that we've done, we were able to kind of section off a 2x2 block kind of all contiguously, right? But for element C here, it's nodes 2 and 4, which aren't right next to each other. Okay. This means that element C is going to go in the entries in rows 2, 4, and column 2, 4. Okay. Okay. And so the entries for that in the table. So let's do row 2, column 2 first. Okay. So row 2, column 2 is actually going to be in this spot right here. So this is kind of a very popular spot. And so let's go ahead and add the upper left entry into there. And so this 250 is going to go in right here. So we have plus 250. Next, let's do row 2, column 4. Okay, so we go to row 2 in the system. So that's D1, D2 row. Column 4 is D4. So that's going to be this spot right here. Okay. And then into this spot, we're going to put in this number right here, which is a minus 250. Next, we're going to go row 4, column 2. Okay, so row 4 of the system, D4, and then we're going to go column 2. And so that's going to be this entry right here. It was kind of in the bottom left of the global system. And so this 250 is going to go there. So let me go ahead and snake this around just like that. So we're very quickly making a mess, but hopefully this is helping to make things a bit more clear. Okay. And then finally, we have to add the last entry there, which is row 4, column 4. And so we go to row 4, column 4 of the matrix, and we end up in this spot right here. Okay. So that's going to give us a positive 250. Okay. So any entries that we're overlapping, we're just going to add them together. And so we're going to do that right here. And so we have 500 plus 100, that's 600 plus 250. That's going to be 850. The brain fart for a second. Let's use rainbow, 850. Power of Apple products for you. Okay. And then of course, every entry in the matrix that doesn't have, that's not boxed or does not have an entry, we're just going to put 0 there. Okay. So I'm gonna rewrite the system right below it just so that's a bit more clear. But hopefully this hopefully this process kind of is a bit clear to you. Okay, so I of course I went pretty slow here, just so that you kind of see every step. But in the assembly step, you're basically looking for where does all the element stiffness matrices go to, and where do I put them into the global system? Okay? Make sure every entry is accounted for. For the springs, it's not going to be that bad because they're just 2 by 2. But then once we start to do 2D problems, and then once we start to do element stiffness matrices that are 4 by 4 or 6 by 6, this gets to be a bit more challenging. So you want to make sure you're really kind of methodical with this to make sure you get every single entry. Okay. All right, let me go ahead and rewrite this, and then just because it'll make the boundary conditions a bit more clear. Oops. Okay. All right. So there is our assembled system. Okay. And so we've gone ahead and added all the elements. All right. Any questions on this so far? Yeah. Yes, it is. Thank you. Yeah. Mm-hmm. All right. So now that we're done with assembly, the next step here is to add our boundary conditions. Because if you try to solve the system, even with the MATLAB method, MATLAB will say that this system is unsolvable. Okay. And so before we can actually solve this, we need to apply our boundary conditions. Okay. And I'm going to use the matrix that I just drew right here. All right. And so we have 3 boundary conditions on this problem. Okay. And so if we look back up at the figure here, we can see here, I'm going to use different colors, that on node 1 right here, node 1 is going to be attached to the wall. And so we have a fixed support or fixed constraint. We have a fixed constraint on node 1. Another thing that we have is we have a load type boundary condition on node 3. as well as a load type boundary condition on node 4. And so we need to do 3 modifications to the global stiffness system for these 3 boundary conditions. Okay, so let me go ahead and put them in colors here. Okay. And so we have the fixed constraint. One. Okay. We have the load of, see, F3 is going to the right. So positive F3 on node 3. As well as a load of minus F4, okay, because F4 is actually pointing to the left, acting on node 4. Okay, so I'm only writing this down just so that you kind of know what colors I'm using, to kind of more easily track what we're going to do in the system. Okay. Okay, so first let's work on the fixed constraint, because that was the first type of a boundary condition we learned how to deal with on Tuesday. Okay, and so to apply a fixed constraint, first we need to see what node that we're acting on. And so in this case, we're acting on node 1. And so that tells us we're going to modify the first row of this matrix. Okay. Right, because the first row corresponds to node 1. And remember, the way that we applied fixed constraints was that we replaced the entire row. And so we kind of got rid of it. So all that hard work we did to get row 1 here, we're going to get rid of it. Okay. As well as the entry on the left. And so now we have a blank first row. And so our entire first row is blank for that. Okay. And then we're going to replace it where we put 1. We put 1 on the diagonal term. And so in this case, the diagonal term for row 1 is the first column. Okay, first row, first column. So we put a 1 there. And we put zeros everywhere else on that row. Okay. And so I'm going to highlight diagonal because I think, if this fixed support was on node 4, what I see sometimes that people still put the 1 in the first column. So you want to make sure you put the 1 in the diagonal entry. Okay? And so in the column that matches whatever row that you're on. And then in the forcing vector, you're going to put a 0 there. Okay? And so by doing that, we force the first displacement, or D1, to have a value of 0. Okay. So that's our fixed constraint. And so the next thing we're going to add is our loads. And remember, the loads are a lot easier. And so we just basically insert these into the corresponding entries in the forcing vector. And so first we have a big F3. And so we have big F3 acting on node 3. So we have F3 right there. Okay. And then we have a load of minus F4 acting on node 4. Okay. So that one's going to go right there. Okay. So the only one that we have left is node 2, but in node 2 we don't have any external forces, and so we're just going to put a 0 for that. Okay. And so last thing we're going to do before we solve is, we're going to replace these by their numerical values. We know F3 has a value of positive 100, and so I'm going to put 100 right here. Okay. And then F4 has a value of 50, so we're going to put a minus 50 right there. Okay. This. Okay, and so what we have is we now have our linear system. And so we have 4 equations and 4 unknowns, and then we've represented this in matrix form. Okay. And so we have a 4x4 square matrix and a 4x1 forcing vector, and we're now ready to solve this. All right, any questions on this before I transition to MATLAB? Okay. All right, and so in theory, you could solve this by hand. And so if you have a if you find yourself savvy at linear algebra, of course you can solve this by hand. But I'm going to show you kind of a faster way to do this, or at least I think it's faster using MATLAB. Okay. All right, and then for the homeworks, I'm not going to assign this homework until after the project's due. But once we get to the homework, you can do the same thing. And so the only thing that I'm going to test you on, and what I'm concerned about, is if you can obtain this matrix right here. Okay, and so if you can show me that you can do the element stiffness matrices, you can apply the boundary conditions, you can assemble it. This is kind of where you stop in terms of hand calculations. And then from here, the way that you kind of take it to the finish line is in math. Okay, so let me go ahead and show you this. And so I'm gonna switch to the computer screen here, but hopefully you have this system written down, because I'm going to show you how to implement this in MATLAB. Okay, so I'm going to go ahead and share my screen. Start it up, MATLAB. Give me a good thing to do. Basically, the idea with MATLAB is that since we have the system in matrix form, we're going to input these into matrices within MATLAB, and then use a special command in MATLAB to actually solve it. Okay. So here we go, initializing, ready. Okay. And so you don't even have to use a script for this. You can actually just do this all from the command window. Okay. And so first thing, and so you need to define 2 entries here. Okay. You write that as a comment. Okay, so the first entry is going to be the square matrix that represents the stiffness matrix. Okay, and 2, you're going to need to enter the forcing vector, which holds the boundary conditions. Okay. All right, so let's go ahead and define both of those. And so I'm going to use a K here, and I'm going to call it K global. Okay, but you don't have to call it that. And the way we're going to do this is we're going to define that matrix row by row. Okay? And so the first row in that matrix is 1, 0, 0, 0. And so we're going to do 1, 0, 0, 0. Okay. And so if you look back on your notes, that's the first row of the matrix in our problem. Okay. Then we're going to enter the next row. And so the next row is minus 500, comma 850, comma minus 100, minus 250. Okay. Notice how I'm using commas to separate entries on the same row. And then when I'm ready to go to the next row, I use a semicolon. Okay. All right, next row is going to be 0, comma minus 100, comma 100, comma 0. Okay. And the last row is 0, comma minus 250, 0, comma 250. Thank you. Okay. And so you can go ahead and enter. And then, you can put a semicolon at the end, of course, but, just so I can check my work, I didn't put it there. And so if you look at this, you can see we have a 4x4 matrix, and it looks exactly like the one I have in the notes, which is perfect. Okay. Okay. And so the other thing you're going to define here is the forcing vector. And so this is a column vector. So every entry here is going to be separated by semicolons. Okay. And so we have a 4-row column vector. So we have 0, semicolon 0, semicolon 100, semicolon 50. Okay. Okay, so that's our F global. And then to get the solution, we're going to make use of this special character. Okay, and so you're going to take K global, which is your global stiffness matrix. Oops, I spoiled it. And so the special character in MATLAB is backslash. Okay, and so it's hard to see. I can't pull it out, but backslash is the symbol right underneath your backspace button if you're working on a Windows keyboard. Okay, and so it's not forward slash. So forward slash is this one. It's backslash. So it starts in the upper left and then goes down to the bottom right. And then after the backslash, you're going to put the forcing vector. Okay, so you do K global backslash F global. Okay, and then when you do that, it gives you the solution. And so the solution here, it's going to give you the solution in vector format. And so this is basically telling us that D1 is equal to 0, D2 is equal to 0.1 meters, D3 is equal to 1.1 meters, and D4 is equal to minus 0.1 meters. Okay, and so that's kind of the easy way to solve linear systems in MATLAB. Okay, and so all you have to do is define the coefficients of the stiffness matrix, define the entries in the forcing vector, use the magic backslash notation, and then that gives you the solution to the linear system equations. Okay? Have you guys used backslash before, or is this kind of the first time using it? Silence, and so no one's seen it before. Good. Okay, I always love teaching other people because it's fun. All right, any questions on this example here? Okay, all right, and so that's the example, and so I don't have any more plans for today. And so just like I promised, I'm going to spend some time. If you're still working on activity 4, I know some people on the Discord were having some issues, and so I want to make sure I address those. And then besides that, I'm going to go around and help people out here. Okay? But if you don't have questions on activity 4, of course you're free to hang out until 6:45. But I'm not going to teach anymore. So thank you everyone for coming today. If you have questions, just go ahead and raise your hand or put something in the chat in Zoom, and I'll try my best to get around to everyone. Okay? So have a great weekend, and I'll see everyone on Tuesday. All right, Will, you had some questions first, right? So why don't you go first?
Okay, do you want me to share my screen?
Yes, go ahead and share your screen.
Okay. Let's
Looks good. Let me help him first, and then I'll help him. All right, so you were getting an issue with the pivot warning, right?
yeah, so like you said to add a bunch of fixed supports, so I just have 4 extra supports.
Yep.
And every time I run it, I still run into the same issue.
Okay.
If I run it right now.
Can I see your connections?
Yeah.
Okay, can you click on each of those? Okay, go to the next one. Okay. Okay, go to the next one. All right, next one. Okay. So, and then go to let me see the last one. Okay. Let me see the fifth one in context. Okay. Okay, I see. So for the 4th and 5th entries in your contacts, what you have bonded right now is the entire beams to the side of the bridge. What do you want to bond instead, or just the endpoints? And so,
okay.
and so mind if I take over for a bit?
Go ahead.
Okay, and so for this one, for instance, okay. All right, so this is those ones. Okay. And so what you want is and it's easiest to kind of click on this vertex mode right here. And so you're going to click on vertex mode, and you're going to click on each of these points right here.
Oh, okay. So it's the actual point of contact.
Yeah, it's a little bit annoying to do with the remote control because there's a delay, but you're gonna click on all the endpoints, and that's gonna replace your contact region here. And so instead of the 7 edges, you should have 7 points or 7 vertices basically.
Oh, okay. Thank you.
Yeah, go ahead and give that a try, and then see if that fixes the pivot. I think what's happening is that it's trying to make a contact between the bridge and the beams, but these beams, it's so far apart from these that it doesn't know what to do. But if you put the vertices here, then it should be able to make the contact.
Okay. Thank you.
Yeah, and Charles makes a good point too. And so when you when you're choosing the vertices, just be careful. Make sure you're selecting the one. So go slowly and make sure you're clicking the ends of the beams.
Okay. Thank you.
Yep.
I'll go ahead and fix that.
Okay. You guys have something to show me?
Yes. This is our prototype. Yes.
Nice. Cool.
Yeah.
Very nice. I don't want to break it.
No, we actually had a guy stand on this.
Oh, really?
On this section right here. So we wanted to show you because this is what we've been using a lot of our answers.
Okay. No, this is perfect for answers. In fact, I could probably replace a lot of this. Although I would try with solid elements first because these aren't super spongy. So I would try with solid elements first. You could probably get a good hex mesh on here just because these are all kind of. How do you have it in the answers? You have these screen?
No, this final product is welded.
Okay.
It's gonna be made out of aluminum welded. Certain sections are entirely solid.
Okay.
So this more
He
than
knows,
the
like,
section
Excel, he
or
knows,
the suspension system is solid because we're trying to do a new system and we're doing
That's what he
hollow
thinks,
front
right?
and back areas
Okay.
for weight reduction.
Awesome. That's great. Sweet.
Yeah. So we rely more on structural designs to make our design strong rather than just materializes.
Nice. Awesome. I love it. Triangles are the strongest shape.
I said, no,
I'm not too big a structural guy, but I know triangles.
Yes,
are
triangles
good. Yeah, exactly. No, it's awesome. Guys. Yeah, great. So this is your prototype, and then you're gonna do testing on this, and then make a final one.
Yeah, we've optimized. I mean, are you gonna ever touch on fluid flow or ANSYS this semester?
I have a handout for it, and so I can the handout's up online. So you can look at it, but I'm not gonna teach it.
This is over here, that's actually what this back area is for. If you notice the two different structures here, we're planning to put fans right here and exhaust fans out here.
Okay.
And then put whole air in to optimize all of it. It's cooling on only the electronics.
Oh, no, that'd be sweet. And you'd be doing like a combined fluid and thermal simulation. Yeah, you can definitely do those in answers. I just don't have that much experience. Because the CFD software I normally use is not. Actually, my grad student, he's just finishing up, but he did his full graduate thesis using CFD and answers. And so he knows way more than I do, but so I thought for a second I should make him teach you, but then he's worked on it for over a year now, so I'm not gonna make him do it. But it's possible.
We were excited. We did a lot of, we're gonna do a bunch more like testing and verifying our data with ANSYS once we get all the final models in and everything. But we want to show you what we've been doing.
Yeah, oh, sweet. That's awesome, guys.
Once we
I'll stand on it after you get the room. I just don't want to be liable for it. I'm worried that's not a good.
This is great.
It is a break.
Yeah. We can stand on
I'm allowed to.
See, if it breaks, I don't want it. That's why I've learned that you don't want to be liable for those things. Who's your advisor? Okay, yeah, I don't want her angrily knocking on my door.
Oh,
That's not a
show
good-
her this today. If you see on.
She's still here.
Oh, we can show her. Yeah, how about we
I'm
go?
not sure which room she's in. but
She's in the engineering building, probably. Although she might not be. She's not in her office.
She's here from 5 to 7 for 490.
Okay, so she's probably teaching.
Bring it over to her.
Oh, well, if she's not teaching right now, you know.
It's 490. It's the most boring class here.
I'm gonna mute this so that no. I already have to do
It's a
this.
special research one.
All right, I'm gonna go help other people with activity board, but let's break that.
Yeah.
I'll take it to her. Her office is on the 4th floor.
Yeah.
Okay, so.
Did you guys really never build a mock-up chassis? Like ever?
Chassis.
This is fun.
Fun.
I mean,
Yes.
I know Redline.
Well,
You've been here
we need
for
help with
on road for a
size.
while, right? No.
I mean, I know.
And this is we need help with
For this one,
size. We're making it
Oh,
a
so it's not like overhaul designs. Like we got.
No, we have, we're just making it, so I know you guys last year were about to, and so instead of making one giant.
The only thing that's.
Making 3
Oh, okay.
separate.
So that's-
Each, Shakespeare.
This chassis, but that's just because it doesn't have the edges cut off anymore.
We're doing,
And
we might be doing
it's
these.
way thicker. So you know how the old chassis is about 5 inches? It's about
Silicone
7.5.
is one of the building blocks for. So planning to do alongside with
So,
Oh, okay.
water extraction from.
oh, and the 3 minute tires, still doing that. Because it just designed.
But they have to show something.
We just discussed about it.
What? Dude, that'd be great. Yeah, actually, this is partially CDR and CR is partially why we do this. So that we could actually display it. Instead of just criticizing like something that we haven't tested yet, we can criticize the actual physical design, draw it, mark it up, everything else.
Because that's hard on the ground.
In person, we're hoping in person, get as many people to take a look at it. It's mobility and chassis, I believe, going.
So instead of that, we still
For like CDR, what first? Hopefully we're doing it right.
That's the default.
we have, so it'll be just be a copy of the first. So the design is,
That's the
there's
only
an
material
auger
that
going
we
down that is surrounded by two, collects the dirt, two brings it back up. The auger releases the dirt inside a container to shake out the finer parts. The bigger chunks goes out, goes out. Yeah.
Honestly, I'm kind of hoping that at least me and my team have done more than previous year's teams. At least in terms of accuracy, because I know it's compared to us. Well, on top of that, I felt like last year, not that they didn't batter anything, but it was they didn't seem motivated to do very much.
Yeah. You don't have people.
So dirt goes into here, it shakes out, big dirt comes out, fine dirt goes into a small weighing section.
Yeah.
That sensor, once it reaches to a certain level, will stop the shaking.
One way to
This
On team.
and I pull out maybe to go over just to get to.
Yeah, I'm really glad I was able to shout at you guys because I provide a lot of information that helps out this year's team, like learning from you guys' successes, learning mistakes, doing like doing things like starting early, being able to more in contact with our team.
Yeah.
How are you gonna test this thing? So let's say test one is alpha, test.
Yeah,
How are you gonna find a way to keep all of that clean with testing?
I mean, we're lucky we met like a lot of like good like right people
Test
that
of that one.
are pulling in a lot of others.
Let's say
That really helps out.
We should.
test is probably.
But yeah, this is insane. Yeah, sweet. And then like even after everything, like when we put the designs finalized, all you guys' critiques put in and everything. Like right now, we theoretically can make the entire system modular. That's what we're really excited about, like the entire electronic system. So I don't know how you guys did it last year, but I know we talked about like one of the previous things like a drawer system, right? Where you pull it out, right? Well, we decided why do that? It's like there's too much space. Why not have all the electronics on the acrylic plate? And then when it comes time to manufacture or do anything,
So when you mean by
pull out the wires, pull out the entire electronic system.
test, we did test it.
Yeah.
Yeah, the drawer thing didn't really work because not space, but I don't know why, but there was a bunch of problems with material and so
And each test site
I don't
is
know
just
if
one
there's
experience.
still an issue, but
Good to know.
they never managed to get like the locking mechanism down properly. So off and then if we turn it, kind of like turn the mechanism into the chassis, so the chassis that they cut out and that would like turn the lock would lock into that. Because it's so precise to use, it's thinking the way out.
And we can't spill chemistry,
And
but we
then,
can spill water.
yeah, it's just didn't work out. And then it did space wise, it didn't really help.
You just found.
The point behind it was like, oh,
But even
we have
then,
more vertical
we
clearance,
still
we
concerned
could
about
add more electronics. I can stack them on time, but that didn't really happen either.
So how are you?
So, well, how we have it this year, and, if you notice in this back area right here,
This is a good.
this back area, right? So that's traditionally where we've stored a lot of the batteries and some whatever else, right? We're thinking of having an actual like tray of all the electronics or all the main electronics that tend to be need to be more maintenance. Put on that tray, so we would actually drill on the acrylic plate, put handles on it, drill specific holes and thread them to where all the electronics would go, right? Once we have that, we would pull down all the electronics as if it's a computer case, right? And when it comes time to like, let's say we need to manufacture, work on the entire like. All you need to do is unbolt the entire acrylic tray from the bottom plate, pull it out, and then you can work on it on a table or whatever. Or even during like competition, you can just pull out whatever component's not working very well. Rather than putting it Velcro down, because I know that, I remember during one of the screen tests that we were running and all of a sudden we lost the Z-axis camera. We suddenly couldn't see, or sometimes it would just stop all of a sudden. I don't know if you remember that, but I do. So we're also thinking like, well, on top of that, we'll dampen the vibrations to the system as much as possible. So our panels have dampeners, like dampening material all alongside it.
Was it 12 people?
Yes, yeah.
I think that one was more.
Because I was planning to make 3 of these.
I know that people
each
are
experience.
like always.
I wasn't aware of the tech for each
Change
experience.
like kind of hold in things.
Right.
Sometimes that's like illegal business.
Okay, so I'll have to look at the other teams, what they do.
Yeah, no.
But I mean, would you say going, I mean, we've done so much more vibration research, but from you, basically a formal number, would you say focusing on vibrations?
Yeah. Better than no.
Yeah.
But Velcro's always meant to be like intended.
So not so.
We're still
So from your own professional opinion, you think that going at it from the vibrations front and bolting everything down front is probably the best.
Have this custom
Yeah, but
science experiments.
It's a good idea.
yeah, it's just a matter of how you go about bolting them.
Yes, the only thing is.
Some of them might be sensitive hardware.
Well, some of these hardwares that
Yeah,
we're thinking, we can treat them as if they, we create housings for them. So they would, slide in, and we would have flavor out where we just keep it down, right? Then we would actually bolt that housing into the acrylic plate. Right, that keeps it in place and it raises up where the fan is able to get to the electronics, or the airflow is actually able to get properly cools it down better.
Even for the last few years.
That's one of the things we did. As for the acrylic plate, for that electronics module, right? We're actually not having an acrylic bottom plate. We have an aluminum bottom plate that the acrylic electronics module bolts on top of. We realized that I know we at the final drop test, we raised up really high and then dropped it and then it finally shattered. So to just mitigate any of that, we just went with aluminum plate. Yes, because
We're not gonna put on.
it has a higher weight
We're just gonna leave it.
amount to it, but the trade-offs are much more beneficial. We can raise up to 10 feet, still drop it, and it'll survive.
Yes, we're accounting for that right now. Since
Well,
we're
ideally, we want to
using
see the electronic side, but yeah.
system, so it should balance it out. The rocker should balance it out. But we don't know anything about this yet. So the thing that's popped in my mind is why don't we just have
Like, make sure you use
a mesh
bolts or like the.
with that.
The hex keys, hex nuts.
So like it'll be like.
They're meant to like, or like.
So once this is done,
There's
this
like
rolls off
they're
the
not meant to.
contaminated stuff, and there's another.
Okay.
mesh.
We'll look into it. We've been researching it because I have from a group, a team, on part of chassis and suspensions,
Just this,
working on
this,
that.
this
Yeah.
part would
So
be
make sure
contaminated.
you kind of just follow the time.
This would not contaminate.
Under
When I'm separating the samples.
But they have.
So the walls will be still contaminated with the mesh. Because this will be rolling.
Oh,
so
it's a
there'll
little
be
rubber
like
grommet.
Maybe a foot.
Yeah. Oh,
mesh.
I think I know what you're talking about.
And the first, there'll be like a section for mesh right here.
Yeah, like to hold it.
Dirt goes through, the next, once the dirt's done, mesh rolls up.
I see.
So
Yeah,
next-
we, I kind of screwed up
Like
there.
a film.
Nope. What? Building chassis.
So
It was definitely a fun experience. I feel like a really
So
proud
it'll be
father
like
or
this. There's a roll of
big
mesh.
game like fish catcher right now.
This,
Looks like holding
not
it.
rolled up. This will be mesh one. This is contaminated. This rolls
Yeah,
up into
I'm
here. And
super
then we
proud
get
of
mesh two coming up.
Like this, I pretty much started during spring or summer and kept at it till now.
We're planning to put a circle. And yes.
So I don't know why, but my team comes up with.
Okay. So I think what happened was, so sometimes what can
We're
happen
talking
when you
about the
click
science.
on the results, when you make a results thing, it's gonna ask you which part of the geometry. If you already have another part of geometry selected, it's gonna pick on that. And so what you can do is just, you can just delete that definition.
The walls is hard.
And then just make it
Either,
And then you'll see in the bottom left, details window, there will be like a geometry. And so you want to make sure that that says all geometries, and not just like one. And so you want to make sure that says like all bodies or all something.
that's too hard. You can't, I can't. We could do water.
What's the bridge?
Yes.
What's the bridge like?
Yeah, this is like a foot bridge.
Okay, I thought about it. I was thinking, I was like, this is a bit of comment.
No, it's not.
Once it's a flush. Mess with the bed. Also,
I don't know.
oh, the weighing.
That's gonna happen.
That thing is still
It's such a weird, it's such a
That will
small
have to
cat model.
rotate as well. That's not hard.
And the road is so, I mean, by itself, it's already so thin. And so one thing that we didn't really talk about is that when we make a wood surface,
Yeah.
it turns it into a paper sheet,
So
but it still saves the thickness of what it was before. And so it saves it as a parameter. So that road is already super thin.
for these,
And so that's why we have to.
I guess they'll have to be
kind of make like this, because we turn it.
the next, each one of these will have.
The road was already so thin, so it's gonna be
Still
bending up.
cross-contaminated.
Even if you have like a thin piece of steel,
The cover part.
if it's already saturated.
This is the door.
That's
It has a sensor for weight. And next these compartments will go on top of these, then that doesn't clean the door itself. It'll just.
That's just to make sure that the bridge, we don't want to over constrain, so you have a fixed both sides that'll create some stresses. And so I picked the Y direction on the zero just to make sure that the road stays. The Y direction's kind of, and I know it looks like the road itself is bending upwards, but that's mostly just due to the fact that, you know, we're doing shells. So the shells kind of bend up for solid shells. In reality, it's actually not, it's still fixed in the Y direction. It's just that we're kind of letting it.
Unless,
That's why that's, it looks like it looks
let's
like.
say
it's
there's a
coming
door
off,
on each
but
side.
it's still attached.
Each
to
two,
it.
These doors have gears on the side that uses one motor to rotate. Say like this is A, it rotates to E.
Zoom people, how are you guys doing? Any questions?
This, it was just stay one motor at a time.
So what you're saying is these three are gonna just shift around. in a
Yes,
circle.
yes.
Okay.
Like a carousel, yeah, because
That's a motor, this is a motor itself. And I've got changing meshes.
this just
changing
rotated,
directions.
yeah.
And that takes away some of the cross contamination.
Some of it, this, it gets, let's see, so cross contamination for the mesh,
And
Done.
walls.
yeah, it's just the walls. The walls is the hard part.
You don't have to worry about walls.
Yeah, airflow, That's the hard part, because it doesn't get, it needs, not just, we could use a high power. However, it does, I know for a fact that it sticks on. You got metal. Silicone. We just do PLA with silicone cover. It doesn't stick. I have to double check that.
Yeah, it's actually hard to find good material properties, I feel like.
Still have sand stuck in them.
Because I mean, it costs a lot of money to do those tests, and so, I can understand, but yeah, it's kind of annoying when you want to do
But
stuff.
as it works, so silicone might have to work. It's a non-stick material, however, it is grippy. To get it smooth, because it's a little. Yeah. Non-stick material, most likely steel, a type of metal. Most likely I'm gonna use just a tin in order to. Well, science is split up into, is now adopted by robotics or the ME part. Science itself or experience is still there. I'm pretty sure, I know for a fact plastics, metal will have to do. Polish the hell out of it. Yes, so we'll have to test that. It has most likely out. Most likely what we're gonna do is take the polish.
You can source that, that's fine. Yeah, you can definitely source that.
While we have 3 controls, we'll also do 3 others. So I gotta make up a procedure. This is not the worst of my worries. And then there's a lot of things Josephine did not go over. Yeah, that's what I've been trying to figure out for the last 6 months, the science.
Structural analysis to the weight of the straight down. Oh.
So glad you guys are still
We
here.
could do that.
After
So it's probably upside down. I think that's if the car was upside down. That's what it was. I don't even know, I don't think this is yours. Oh, here's mine. Yeah.
maybe
Well, actually, yes. So structural, so I think it's like if the car was upside down, you put all the way on top. So we could definitely. At least- Talk really quick. We could do it on last year's test. So break that.
doors on.
We don't even have that. We could just do. You're buying. Make up welding series.
That's it, because I know for a fact, we're using the pumps from last year, from the old system where it pumps the liquid in here.
I was wide.
Hydrogen, you had a.
the silicon extraction. We're trying to do some research on that right now because I know Mars is currently doing the silicon. Once there's silicon, there's life. We might not do it since we mentioned that. We might just stick with the fluorescent light that you guys. Because we're getting a spectrum. Putting thousands of this one number out. We have to make these. Each one has a camera, except the third one have a spectrum version camera. We're planning to use in regular times. We still have some. Think about this. Does it cause constipation? Because
If they can get into the pipe, it's gonna cause
so I'll just have this top. Well,
are not open.
okay.
So let's say this is your.
Well, that's where the doors come in, because each one has a door at the top.
When you apply the
In order to keep not contaminated. Doors will be elevated maybe a centimeter, so open up, close back down. So we'll have to talk to the enemies about it.
So let me see.
We're pretty sure Mario was
Yeah, either that or we just have it covered up here, just have this open. This will reduce, this has to be open. The second, we can use the other thing is that we can change this. This was originally designed to be aluminum. So if that's the case, we just change this whole thing to acrylic, just like yours. Except we, instead of bolts, we'll just use aqua tape, fish tape glue in order to actually put it together.
Hey, whatever works.
Yeah.
As long as it doesn't get any stuff.
It's much lighter than bolts and nuts.
Unless you get in there.
Easier to repair than brakes. I'm assuming this is the three of these would be still much lighter than what we have for the current robotic system. Fishbowl.
Whatever glue.
Oh, yeah.
Why'd you choose that?
How does the zip ties are on there, duct tape's on there too.
It's not actually moving up. Because we turned this into a shell. Remember, one of the additional things with the shell. is
Give it a competition. Duct tape.
That's what we're.
Duct
Some
tape
of
is
them will
friends
say
of it.
duct tape.
It's not actually. It's actually whatever.
I'm just
Make it
gonna,
a bullshit. That's what that comes down to.
actually duct tape, no, I actually worked in space, but how is duct tape is made out of resin? Yes, resin and wire.
One that was just-
Yeah.
Just so it's
Duct tape
like a
is-
bullshit. That's basically why.
So, I'll figure out.
And then go after the virus, because they're gonna get killed the hardest, and then the science.
Yeah, I know. Well, science is going to last because we need to prepare more robotics. Summer.
I remember. Robotics, you go, real.
For PDR.
And then mobility went, and they got,
Where did Josephine?
she was in science with me.
So she didn't have to experience everything else. She had to experience everybody else's painting.
Yeah, she was too little, so it kind of after her a bit. But since she was like, I'm more so into science, we kind of. And no one wanted to be there, so we just.
Change the sizing for a little bit different.
Alright.
People did have,
Change it here. You'll change it.
alumni science.
But if you
They
make the
have
sizing
it
up,
in their,
size.
arguments, but it wasn't like killer like you are at the beginning.
Right.
Get you.
I
If you
actually,
want really
actually-
big feedback, go first.
I actually will do feedback on this. This is a new system.
Go first. Get killed.
I'm gonna go first for this because we haven't had a working sign system in years. So I
So you
need.
go first. and get
Yeah. I'm gonna take a picture.
All right, guys, we're out of time. So, so if you have any more questions on activity 4, just email me. So, you guys have a good weekend. I'll see you guys next week.
I know, I didn't do anything, I was hoping.
Alex.
All right, I'll see you guys next week, Zoom people.
Just a one. I got rid of it.